It's a continuation of looking at matrix operations. We had looked at matrix times a vector. There's two ways to do that. Let me focus on the first way just one more time. Remember how it worked. To get each row of the output, we look at the corresponding row of the left-hand object that we're doing. Here was a matrix, and here this was a vector. And we pair the entries of that with the entries of the column vector. And so I tend to picture these things rotating into place, so the 2 matches the 4, the 3 matches the 5, the 1 minus 1 matches the 6. Or you can picture this guy rotating into place and matching. It might be even better. 4 times 2, 5 times 3, 6 times minus 1. Those all combine to get the one number, the 17 here. Then you repeat it for that row and that row to get this entry and this entry. Well, matrix times matrix, you can think of as doing it in the same way. And I'm just going to copy this over and blank them out. It's often quicker than just setting up a blank matrix by hand. Okay, and what we're going to do in this way of multiplying them together is to get the first row, first column. Let me write this down. First row, first column of the output. We're going to go first row of the left-hand matrix. Let's call that A. So let's see, this is just going to be A times B equals, let's say C. And the first column of the right-hand one in the product, that's B. And we're going to pair them up in exactly that same way. 4 times minus 2, minus 8, plus 5 times 0, so minus 8, minus 6 is minus 14. Okay, so the scratch computation there was 4 times minus 2 plus 5 times 0 plus 6 times minus 1. I guess I'll put a little star there too to make it all parallel. Okay, and that was equal to minus 14. Now what about the first row, second column of the output? That's the first row still of the left-hand one, A, and we pair it up with the second column of the right-hand one, which we're calling B. Scratch computation is 4 times 3 plus 5 times 4 plus 6 times 2. Oh, those are times, sorry. Times 2, there we go. So 4 and the 3 match the 5 and the 4, the 6 and the 2. And that is going to be 12 plus 20 is 32 plus another 12 is 44. Let me just do one more by hand. Let's say we wanted to do the second row, third column of the product, the output. I guess I should, yeah, it's the product. That's going to be pair the second row of the left-hand matrix paired with the third column of the right-hand matrix, B. Okay, so that's this. We're going to get this entry by pairing up, let's do the scratch calculation, 7 times 2 plus 8 times 10 plus 9 times 5. And I screwed that up. Plus, it's hard to do that while I'm looking at something and talking, etc. Okay, so 80 plus 49. Let's see, 80 plus 45 is 125 plus 14 is 139. And so that entry is going to be 139. So for every entry, all 12, you've got to do a computation like this. It's a fair amount of work. So for example, to get this very last entry, we would take this last row with the last column. To get this guy, we take the last row with the first column. To get this guy, we take the middle row by the second column. All together, it is this guy. Let's see if we did the ones right that we actually did. Oh, we did. Yeah, we got the 3 entries right that we actually calculated by hand. So this is a fair amount of work, but it's a fairly formulaic, simple procedure once you do it a few times, the row by column. So that's one definition. the way I introduced it was actually a bit of a different idea, and I won't do the computation right now, just to make this a nice short video. But the idea there is you can actually do it just by doing this process, matrix times vector, 4 times. You can take this matrix times this vector, and that will produce these 3 numbers. These numbers do not come into that process, because all these guys, the first column, it says match whatever you have here with the first column of this guy. It never mentions these guys. The second column here is produced by taking matrix times vector, just this whole matrix times this column vector, and so on. This vector is produced by this matrix times this column vector. This vector is produced by this matrix times this column vector. And then you can use either definition of column vector, a matrix times vector that you like. Usually, if your main goal is just to get the answer, your best bet is in matrix times vector to use this row by row method, which just goes entry by entry, and in matrix times matrix to just go entry by entry by entry and use this method of just pairing up row by column, row by column, row by column, row by column. It's not particularly, doesn't illustrate much, but it's a good way to just get the answer when you need to do it. We're not going to do a lot of it, but we want to get a taste of it because it does lead to some very cool ways of thinking about equations. And if you ever come back to linear algebra, which I hope you do, it's a beautiful subject, then it'll be very useful.